Hi everybody, welcome to another video in differential equations, section 8.2. Before we study more about power series and differential equation, we just need to go over a few things about power series. Right, power series. Power series about the point x0 is an expression of the form. So this is what makes it power series. We have the power of x minus x0 to the n, and then the coefficient a sub n. N goes to 0, from 0 to infinity. X is the variable and a sub n are constant called the coefficients of the power series. The power series converges at x equal to c if the limit of this exists. Otherwise, it diverges. If the sum equal to a number, a finite number, then it exists. If it goes to infinity or negative infinity or does not exist, then it diverges. Right. Radius of convergence. For each power series, there's a number rho between 0 and infinity called the radius of convergence. The power series such that the series converges when x minus x0 less than rho. So the reason we call that is the radius of convergence, because we have x0 is at the center and rho is the radius of convergence. So we go rho on the left side, rho unit on the left, and then rho unit on the right hand side. By the way, that's again is the Greek letter rho. Right, so it will be convergence if x between this interval, because at this point we can say it x0 plus rho, x0 minus rho on this point. So if x between these 2 points, or x minus x0 less than rho, then the series is convergent. If it is on the outside, it will be divergence. If the series convergence for all value of x, then the rho equal to infinity. Right, a ratio test for power series. By the way, if you're taking calculus 2 with us, at our course using the most common calculus book, we will not write the power series in this form. Right. Now, the ratio test. Now there's 2 versions of it. Now let's look at the first version, this one. If for large number n, the coefficient a sub n are non-zero and satisfied, so the ratio here we have a sub n divided by a sub n plus 1. It's not quite like what we have in calculus 2. Right. Then the radius of convergence is equal to rho, which is equal to L. So we just take the ratio of this term divided by the next. That will be the radius of convergence. Right. This is what we have in calculus 2, slightly different. So in Cal 2, in calculus 2, what we have is that we have the series of b sub n, and of course go from 0 to infinity. Now the series is convergent, but rather than divide by a sub n divided by a sub n plus 1, actually we should put the absolute value 2. Rather than take this term divided by the next term, we do that in reverse. So that will be rather confusing if we use the same L here. So let's use something else here. Okay. Right. Now, if the ratio of the next term divided by this one is equal to k, and if k is between 0 and 1, then the series is convergent. By the way, if it is positive term, we can just roll on absolute values. There's no problem with that. Right. Now notice the difference here. If you have the ratio of this term divided by next, that equal to L, and that gives us the radius of convergence. Alternatively, if we take the next term divided by this equal to k, of course when we do that, that's going to be a little bit different. If we try to write, in this case, if we write b sub n is equal to, if it is equal to the power series, then b sub n equal to a sub n, that, and b sub n plus 1 over b sub n. If we write out, we have a sub n plus 1 over x minus x naught over a sub n to the n plus 1, sorry, x minus x naught to the n. That is the ratio of b sub n plus 1 over b sub n. Right. Now what we let's take the absolute values there and here. When we cancel x to the x minus x naught to the n power, and we cancel this with n of them, we left with x minus x naught. So when it cancels out, we will have a over n plus 1 over a sub n, and then we have x minus x naught. And if it is convergent, if it has to be less than 1, and multiply reciprocal, so we have x minus x naught less than multiply reciprocal a sub n plus 1. So we have to flip the fraction to move to the other side, right? And this is equal to L, which is the radius of convergence. So that's why there's the corresponding between these two, but this is not L. If we're going to write in this form, which is perfectly fine, the next term divided by this term, absolute values, it will have x in it, and then we have to solve for it to get the radius of convergence. If we write a sub n over a sub n plus 1, then whatever we have is going to be the radius of convergence. We don't have to do like this. Later on, if you go to engineering, I'm not sure what formula they will use, but of course when they talk about ratio test, it could be either one of this form. Right. The first example here, I'll try to show both of these forms. Right. Determine the convergence set of this. Right. So notice that if we first we're going to use the form here, a sub n over a sub n plus 1. So if that is the case, we will ignore the power term, so that will be a sub n with, and then we take the ratio of a sub n divided by a sub n plus 1 inside absolute values. So we do that, divide fraction, multiply reciprocal. We're going to flip that and cancel out. We end up with this. And then we're going to split absolute values of 1/2 or negative 1/2, still 1/2. And then we have n plus 2 over n plus 1. Now as n goes to infinity, so all of this, both of them have n goes to infinity. N go to infinity, this go to 1, right? When n go to infinity, n is extremely big. N plus 2, it's just n, because n is too big. N is 2 is insignificant compared to n. Same thing, 1 is insignificant compared to n. So because n goes to infinity, the highest power matters. And we just have n over n cancel out, which is 1. So this equal to 1/2 equal to L. So that's why the radius of convergence is 1/2. Right. So we write the radius of convergence is 1/2. Therefore, the series convergence, if it is x minus the center, x minus 3, the center, is less than 1/2, or if we solve for it, we can say x minus 3 less than 1/2, but greater than negative 1/2. And then we'll plus 3 on everywhere. That gives us 5/2 over x. 5/2 less than x, less than 7/2. So that's what we have here. Right. And finally, we know that it is convergent between 5/2 and 7/2. We're not sure what happened at the endpoint. So we let x equal to 5/2, and we do that. We have negative 2 to the n and negative 1/2 to the n. Those cancel out. We have 1 over n plus 1. This is a harmonic series, will be divergent. Now, x equals 7/2, same thing, do that. And that cancel out, we have negative 1 to the n power over n plus 1. This is alternating harmonic series, which is still convergent. So the series is convergent. Right. So that's what we did using the first form. Now I use the alternative form. Either way works. So notice that we have the series so this is the series. Right. Now, rather than use a sub n where we ignore the power terms, I'm going to keep the whole thing and call that b sub n. So first, let b sub n equal to the whole thing. Right. Now the ratio test, if we use this form, we take limit at n goes to infinity, b sub n plus 1 over b sub n inside absolute values, and this have to be less than 1 for it to be convergent. If it is equal to 1, it will be inconclusive. If it is bigger than 1, it is divergent. Right. And it makes sense, right? Because if the next term divided by this term is bigger than 1, the next term could be bigger than the previous term. Therefore, the terms just keep getting bigger and bigger. In that case, we do not have the finite sum. Right, but this is what we have here. So limit n goes to infinity, b sub n plus 1, I'm going to put n plus 1 into here. Right, so negative 2 to n plus 1. Here n plus 1 is n plus 1 in for n, and then plus 1. We still have x minus 3 to the n plus 1, all of which over negative 2 to the n plus 1, x minus 3 to the n. Right, multiply reciprocal. Still absolute values, negative 2 to the n plus 1, n plus 1 plus 1, so that n plus 2. Multiply reciprocal, n plus 1 at the bottom, stay on the top, negative 2 to the n to the bottom, x minus 3 to the n, sorry, I forgot, x minus 3 to the n. -2 to n plus 1, right? And then I forgot the x minus 3 to the n plus 1. Just like this, we should have x minus 3 to the n at the bottom. Right, try to simplify. -2 to the n, -2 to the n plus 1, cancel out, we just have -2 on the top. X minus 3 to the n plus 1 and x minus 3 to the n, that cancel out, we have x minus 3 on the top. And then n plus 1 over n plus 2, cannot do anything with that. What's next is that this is limit of n goes to infinity. We can take anything that is not n outside of the limit. Not only that, outside the limit, outside the absolute values. So if we do that, we cannot just take anything outside absolute values. It could be negative. Just to guarantee that, we're going to put absolute values of -2, x minus 3. So we're going to take this outside of the limit because that doesn't have n in it. So take that outside, but to guarantee that's still positive, I'm going to put it on the inside the absolute values, and then we have the limit as n goes to infinity, n plus 1 over n plus 2. Right, we talk about this. As n goes to infinity, 1 is negligible, 2 is negligible, right? Infinity plus 1, still infinity. Infinity plus 2, still infinity. So that's why we can just ignore the 1 and the 2. I don't want to do that, but at n go to infinity, that cancel out. And we just have, by the way, to guarantee this positive, I can take the 2 outside, and I'm just going to write like this. Absolute values for everything. And now the limit. We just say that n goes to infinity, so 1 is negligible. So I just say the limit is n over n, right? Because n plus 1 or n plus 2, as n go to infinity, the plus 1 plus 2 doesn't really matter. N over n is 1, so this pretty much equal to 1. And absolute values of -2 is 2 and x minus 3, right? So the limit of that equal to this. Now, next important things. If we want this to be convergent, this has to be less than 1. Because of that, divide by 2 on both sides. So x minus 3 less than 1/2. Divide by 2 on both sides. And this one is the radius of convergence. Radius of convergence. Of course, if we have before, that's also 1/2, so that's exactly what we have. Right, the rest of the problem will be similar to it, so I'm not going to write it out. But I'm just going to write 2 different forms of the ratio test. Both of them give us the same thing. If we take the whole thing to be b sub n, it's going to be the next term divided by this. If we're going to ignore the power terms, it's going to be this divided by the next one. So there are 2 different forms here. The advantage of writing a sub n over a sub n plus 1 give us the radius of convergence right away. When we write like this, embedded in it, we will have x minus the center, and then we're going to write like this, and therefore we can say 1/2 is the radius convergence in this case. So either way, that should be the same thing. Alright, I'm sure you will see this again in some different form. I'm not sure if it is in this or that, so I'm going to write both. I mean, not in this class, maybe an engineering class or science, some different kind of high level math or science. You might see this again. It might be different form. Right. Now, But this only gives us the radius of convergence. We still have to check for the endpoint. What happened at the endpoint? Right. Now this determine the interval of convergence for this series, right? So yeah, if we have space, if we have enough space, I'm going to do both. Right. So first, if we use a sub n, that means we'll ignore the power term. So it's a solution 1. If we let a sub n be the term without the power 1 over n to the 5th 6 to the n, right? And then we will have, if we have used a sub n without the power term, then we'll take the limit at n goes to infinity of a sub n over a sub n plus 1. And whatever this equal to, give us the radius of convergence, right? A sub n is going to be this 1 over n plus 1 to the 5th and 6 to the n plus 1. This is a sub n, right? And then over a sub n plus 1, n plus 1 instead of n. Then 6 to n plus 1. Right. Multiply reciprocal. I'm going to flip this. Right. 6 to the n plus 1 over 6 to the n, they cancel out. And we have 6 left. And then n plus 1 to the 5th and n to the 5th. Cannot really simplify that. So I'm going to say n plus 1 to the 5th over n to the 5th, right? And then times 6, n to the 5th times 6. Since both of them have the power of 5, I'll bring them inside. Power, and then 6. By the way, as n go to infinity, n plus 1 and n almost the same, right? Infinity plus 1 is the same as infinity. So in that case, the inside just 1. So all of this we have 1 to the 5th power, which is 1. Because as n goes to infinity, n plus 1 is equal to n. So we have n goes to infinity and we have 1 times 6, which is equal to 6. So the radius of convergence is 6. By that, I mean the power term x minus 7 will be less than 6. Alright, this is solution 1. Now, if I use the b sub n, if we let b of n including the power term, and we do, if we take the whole thing, including the power term, it will be b sub n plus 1 over b sub n. Right. Right. First we want to put n plus 1 in here. X minus 7 to the n plus 1 over n plus 1 to the 5th, 6 to the n plus 1. Yeah, replace n plus 1 into n, and then over b sub n, which is the same thing. Right, with that, then multiply reciprocal. X minus 7 to the n plus 1 over n plus 1 to the 5th power, 6 to the n plus 1, multiply n to the 5th, 6 to the n, x minus 7 to the n plus 1, x minus 7 to the n, sorry. Right, what can we simplify? 6 to the n, 6 to the n, 6 at the bottom, right? X to the n minus x7 to the n, x minus 7 to the n plus 1, we have x minus 7 on the top there, and then n to the 5th and n plus 1 to the 5th stay there, cannot really simplify. So we will have the limit as n goes to infinity, x minus 7 n to the 5th, n plus 1 to the 5th. That's gone, but we still have 6. Right, now, just like what we did earlier, we will group these two together. And the x minus 7 and the 6, we can take it outside the limit because that doesn't have n in it, right? But when we take it outside the limit, because it is under absolute values, it will still inside the absolute values. So to guarantee it's still positive. And both of them have the 5th, so when we take it inside, once again, as n goes to infinity, this one goes to 1 to the 5th power, which is 1. So we have absolute values of x minus 7 over 6. We can split absolute values. Right. Now, if we run this form, the series convergent if this is less than 1. If less than 1 for the series to be convergent. To converge. We need that less than 1. So multiply 6 on both sides. We have x minus 7 less than 6. And with that, 6 is the radius of convergence. That is exactly like what we had before. So that gives us radius of convergence. Right. So both solutions give us the same thing, x minus 7 less than 6. Right, we go from there. Now, of course, we know it's going to be the center 7. We go 6 on the left, 6 on the right, right? So we have x minus 7 less than 6. That means x minus 7 less than 6 but greater than negative 6. Plus 7 on both sides. So we have 1 less than x less than 13, right? Because that's easy to see. If we have center at 7, plus 6, because 6 is the radius convergence, plus 6, this of course will be 6 plus 7 will be 13, and we subtract 6, 7 minus 6 is 1, so x must be between 1 and 13. So we know it is convergent between 1 and 13. The next part of the question is, what happened at x equal to 1 and x equal to 13? Well, we have to check it. So at the boundary. So next, for x equal to 1. Of course, we're going to put 1 back into the original series. Right, so we have that. Give us 1 minus 7. We have minus 6 to the n. Right? I can split that as negative 1 to the n, and then 6 to the n over n to the 5th, and 6 to the n. Cancel out. That's what we have. And this is a p series when p, actually not just p series, alternating p series. So this definitely convergent. Right. So for out, this is negative 1 to the n, so alternating series, decreasing, and the last term goes to 0. So for alternating series, two things need to happen. Just have to write this out. This is the alternating series. Where b sub n equal to, ignore the negative, two things happen. B sub n goes to infinity as n go to infinity. So yes, at n go to infinity, that check. Next, b sub n is decreasing or non-increasing, I should say. But this one decreasing because the bigger values for n, the smaller values of b's of n. So this is decreasing. So we check when both of them check, this is convergent. So both of them checks, so this is convergent. Right. So x equal to 1 is convergent. Next, for x equal to 13, I'm going to put 13 in for x. Minus 7 to the n to the fifth, 6 to the n, to the n to the fifth, 6 to the n. 6 to the n cancel out. We just have 1 over n to the fifth. Now, this is a P series where P equal to 5, which is convergent. The P series when any power that is less than, any power that is greater than 1 is convergent. So P series P equal to 5, which is greater than 1, so it is convergent. So either case equal to 1 or 13 is convergent. We know between 1 and 13 convergent. So the interval of convergence. So not only it is between 1 and 13, it could including the 1 and the 13 as well. So that is the interval convergent if we're going to write as an interval 1 and 13. Right, so we use the ratio test either in this form, whatever the ratio, whatever that limit goes to, that will be the radius of convergence. If we include the power term, then we have to do a little more work, but ultimately we should get the same thing. And then we have the radius convergent. The center is 7, so it goes 6 on the left and 6 on the right. We have 1 and 13, so we know it's between 1 and 13 it is convergent. Just need to know what happened at boundary. So at boundary x equal to 1, we can show that it is convergent. At x equal to 13, that also convergent. So put that together, it's convergent at 1 and 13 and anywhere in between. Right. Yeah, this might be a while since you're taking calculus 2. But like I said, the focus on this section is we use the power series to write a solution of differential equation. So it's not pretty much this. But we have this section and the previous section just to familiar with the series and how the series works. Right. Now keep working with series. Here are a few things that we have. Right. If we write the series in this form, has a positive radius convergent rho, then the function is differentiable and the term-wise differentiation is. Now if we take the derivative of this, of course take the n down and then original power n minus 1. But just notice one thing when we take derivative, when we differentiate the n equal to 0 here, we go to n equal to 1. This is not a typo. Whenever we differentiate the index will shift into 1 like that. Now of course, now if we write it out, it will make sense. If I have the power series, I'm just going to say a naught plus a1 x, just use x, or x minus x naught, it doesn't matter, but I just use x. Let's say center 0 plus a2x squared. Notice that, of course, I can write the power series using the Taylor series. This is the Taylor series when we use the values of the function embedded in that. But no, this is just a power series in general. Just have a0, a1, and a2, and so on. If that is the case, when we take derivative, of course, derivative of a0, derivative of constant is 0, so we just have a1 plus a2 2a2x, and then 3a3x squared, and so on. So that's we end up with this. Of course, we do not have the a0 anymore. We just start from a1 now. That's why when we take derivative, the index will shift, will increase by 1. Right. And when we integrate, we just integrate, and index still the same thing. So we can integrate term by term, or differentiate term by term. If when we differentiate, the index will increase, will shift, not increase, but shift. Right. Function is said to be analytic at x0 if an open interval about x0, the function is the sum of the power series. That means there is a power series representation for the function at that point. We'll revisit this later. But what we have now is some Taylor series, or in this case, for these three, this is the Maclaurin series center at 0, we just have x. This one center at 1 because we have x minus 1 to the n power. So this one center this one x equal to 1. And all of this, the center at x equal to 0, or we call this is, these are Maclaurin series, Taylor series centered at 0. Which means we call this Maclaurin series. Right, so those are common series. Alright, so this is common. Look at the sine, cosine first. By the way, the ln of x, that's different story. There's a way to do that too, but focus on the sine, cosine. Sine is an odd function, cosine is an even function. That's why an odd function you see on the x to the odd power, right? And then, because if we want to, so just on the odd power of x over all the same factorial, pretty much. And we put them together, this is what we have. And cosine is an even function, so we start with x to the 0 power over 0 factorial, which is 1, right? 1 here, this one can be the first one here can be written as x to the 0 power over 0 factorial. Bottom line is cosine is an even function. It will be sum of all of the even power of x over the same factorial, and that will end up with this. Right, so that is sine and cosine. A to x, it's just like the combination of all of this with all the positive. But there's all of them are positive, and we just have 1 x to 0, x to the first, x squared, x cubed. So we just have x to the n over n factorial. Right, so that's what we have. The remaining of the section, we're just working with the power series. How do we multiply? How do we divide? Actually, adding or subtract is a lot more important, but we do that in the next section. The remaining section, we're just working with derivative, multiply or divide, because adding the power series is essential. It's a lot more important. We study that in the next section. Right, so first, use the power series to show that derivative of cosine of x is equal to negative sine x. I make a mistake, so I have to do this again. So once again, we start the series for cosine. which is this one. Right. So cosine of x. Try to write small because we don't have a lot of space here. Cosine of x is an even function. I should have to dot. It's an even function, right? So all of them in the even. Once again, try to write small. Probably we don't even have enough space here. Right. Now we take the derivative of everything. Derivative of cosine of x. Derivative of 1, 0. Derivative of this. We have negative 2x over 2 factorial plus 4x cubed over 4 factorial 6x to the 5th over 6 factorial. Now as for the summation, we do the same thing, we take derivative. But most important, when we take derivative, it is no longer n equal to 0. The index has to shift 1. So instead of n equal to 0, when we take derivative, it will start from 1, increase the index by 1. Right, so we have negative 1 to the n, and here we take down the 2n, x to the 2n minus 1 over 2n factorial. Right, how can we simplify this? Right, notice that we have a number divided by the factorial. So what if we have n over n factorial? What's that equal to? Well, n factorial we can write as n times n minus 1, n minus 2, all the way back to 1. Cancel out the n, we have 1, and all of this we can write as 1 over n minus 1 factorial. Right? An example here, let's say 10 over 10 factorial. 10, we can write 10, and then 10 here will be 10, 9, 8, 7, all the way back to 1, right? And the 9 all the way back to 1 here can be written as 9 factorial. So 10 over 10 times 9 factorial, cancel out the 10, we have 1 over 9 factorial. Right, so that's what we have. So same thing here, this gives us negative, this is 2 and 2 cancel out, so just minus x plus x cubed over 3 factorial. 6 and 6 factorial cancel out. We have x to the 5th over 5 factorial plus. Now, the index here does change to 1. How do we change back into x? So in that case, let's try something else, different index. Let's say instead of n, we use k plus 1. Why do we do that? So the index will go back to 0. So we need something that's 0. So instead of n, let's say n equal to 1. So we have n minus 1 equal to 0, right? So in that case, we will let k equal to n minus 1. So it will be equal to 0 for the first value. And because of that, n is equal to k plus 1. Right. Now, if we change n equal to k plus 1 into this series, what do we have? Now, instead of n, we have k plus 1. By the way, we'll do this quite a few times later. So this is certainly helpful. By the way, 2n and 2n cancel out. Indeed, we do have 2n minus 1, right? 2n minus 1, which is 2. To n minus 1 factorial. Because the 2n cancel, the next will be 2n minus 1, but n equal to k plus 1, so that's what we have at the bottom, is that. And then 2n and 2n cancel out. On the top we have x, and 2, n is k plus 1 minus 1. Right? Subtract 1 on both sides, k will be equal to 0. Yeah, but just substitute all that, so we have, and I also factor out the minus. So we have x minus x cubed over 3 factorial minus plus x to the 5th over 5 factorial dot. That should be subtract. Of course, now you can see that is the series for sine, so derivative of cosine is negative sine. Right. Now how about the series? K plus 1 equal to 1, so k equal to 0. Right. The negative 1 to the k, we can say negative 1 to the k. And then negative times negative 1. And then I just put the negative 1 on the outside. Right? Negative 1 to the k plus 1 is negative 1 to the k times negative 1. The negative 1 I move in front. And finally 2k plus 2 minus 1, 2k plus 1. And once again x to the 2k plus 1. Now, if you look at this series for sine, here, instead of n, we have k. That is exactly the negative, except for the negative sign. This is the series for sine. Instead of n, we have k. So when we shift the index so that this will have k equal to 0, we start the series needs to start 0. It will be identical to the sine except for the negative. So that's why this is equal to negative sine x. Yeah, we will do this kind of things a lot later. So when we try to change the index, so to satisfy some certain things, right? So once again, 2k plus 2 minus 1 plus 2 minus 1 is plus 1. That's what we have. Right. Now, this is something that we haven't done in Calc 2. Write the first few terms of the Taylor series of e to the x times cosine of x. Or I think we could do that in Calc 2 also. So write the first few terms of the Taylor series of e to the x times cosine of x. Right, how do we do that? So we have e to the x times cosine of x. Right, now I write first the power series for e of x. By the way, if we just want the first few terms, but when we multiply this, it cannot be the summation. Summation, we cannot just multiply them. It will be very difficult, if not impossible. So I just want to write the first few terms here. E to the x, the power series for that is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So that is the power series for e to the x. Now, for cosine of x, the power series of that is on the even function, right? It's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th factorial, and so on. Right. Of course, we're going to multiply it out, but I will rewrite this, simplify the fraction by just one bit. Right. 1 plus x plus 1/2 x squared plus 1/6 x cubed plus, and then multiply by 1 minus 1/2 x squared plus 1 4 factorial 24 x to the 4th = 6 factorial, I think 720. Now just multiply. Of course, when we multiply our combined like terms, pretty much that. However, when we multiply this, we should statistically just combine like term at the same time. In this manner. First, how do we get all the thing as constant? The only way we get the constant term is by 1 times 1, right? So first, the constant term 1 times 1. That's the only terms, that's the only constant term we can have. Right, next. So we have the constant. Now, do we have any x? And how do we get x? Well, the only way we get x is take this x multiplied by 1, right? To just write all the possible way you can get to the power of x. Right? X and 1. That's the only possible combination to have x. Because we cannot just multiply the whole thing in combined like terms. That could be too much. Right, like this is more systematic. The constant have to be 1 times 1. The power of x have to be that. Now, the next one is interesting. How do we get x squared? To get x squared, we can take this x squared times 1, right? So I will write 1/2 x squared times 1. Or I could take this one multiplied by 1 multiply this negative 1/2. Or we have 1 negative 1/2 x squared. That will also give us x squared, right? So these two terms give us x squared. Next, how about x cubed? How do we get to a cube? To get to a cube, we can take this cube multiplied by 1, right? Or we can take this x multiplied by that. Actually, we just look for the first one. Take this one, multiply any of this. Can we get a cube? Nope. Go to x. If we use this x, multiply any of this, which one will get a cube? Well, it will be this guy. So if we use x, we have to multiply by negative 1/2 x squared to get to the x cube. Right, that's done. Now if we go to this one, can we use this one multiply somewhere to get to the x cube? Any of this? That could be no. So go to the next one. This one, can we multiply with this to anything of this to get x cubed? The answer is yes. That would be 1. Multiply by 1. These two terms give us an x cubed. Now, how do we get x to the 4th? To get x to the 4th, if we start with 1 here, can we multiply any of this to get x to the 4th? The answer is yes. This guy. Okay, there's only one term. We have some certain condition. Now go to x. If we use x, multiply any of this, can we get x to the 4th? That would be no. So skip that. Go to the next one. If we use 1/2 x squared, multiply any of this, do we have x to the 4th? The answer is yes. If we multiply that with this term. So just pick one term here and then one term there to have x to the 4th. Alright. Next, this one cannot give us x to the 4th by multiplied by this. It's not going to help. So we have to take the next one. Actually, we need one more term. 1 over 4, x to the 4th over 4 factorial. 1 over 24 x to the 4th. That x to the 4th have to multiply by 1. All of this give us x to the 4th. Now the rest we just simplify. 1 times 1 is 1 plus x. Negative 1/2 x squared. 1/2 x squared, that cancels out, so that's we don't have any x squared. Negative 1/2 plus 1/6 x cubed. So what is negative 1/2? Plus 1/6. Should be negative 1/3. Right, and then how many x to the 4th we have? 1 over 24 minus 1 over 4 plus 1 over 24. Alright, fraction negative 1 over 6 x to the 4th. And we can just go like that. So rather than just go ahead and jump right into it and multiply everything and combine like term later, we keep in mind of combine like terms. Right, to get a constant, we use 1, multiply any of this to get a constant. Yes, multiply by 1. Next, to get to x, if we use 1, we won't be able to get anything into the x power by multiplying 1 into this. But if we use x, multiply by 1 will give us power of x to the power 1. Now x squared, we start with 1, we can multiply by negative. Or if we start with this term, we can multiply by 1. And then just find a combination that gives us the particular power of x. Do that, it is more systematic way to multiply them out. So next, write the first 3 non-zero terms for tangent of x. Well, tangent of x is equal to sine over cosine. Now this time we have to divide. So how do we divide the power series? Right. So this is just like when we do the long division. So cosine x go to sine x, right? Just in case, how do we divide? For example, let's say 56 going to 1 2 3 4. That means 1 2 3 4 divided by 56. Of course, whatever the quotient here we're going to put there. So we write like that. So cosine of x going to that. So we say cosine of x. Yeah, we're going to write like that. So cosine is an even series. 1 minus x squared over 2 factorial. I just want 1/2 x squared plus 1/4 x to the 4th minus 1/6 x to the 6th, and then so on. Divide. Now into sine. Now notice that this we have to leave some space. It's for a placeholder. Right. Sine x is an odd function. X. Some space because there's no x squared there. Minus 1 3 factorial. Sorry. 2 factorial is 2. 4 factorial is 24. 6 factorial is 720. So minus 1 over 3 factorial. And then x to the 4th, there will be none. And then x to the 5th will be 1 over 5 factorial, 120. X to the 5th. Right. So we divide power series like this. First, divide the highest power x divided by 1. X divided by 1. Take the highest power divided by x divided by 1 is x, right? So we take the highest power, x divided by 1 is x. I'm going to write here. And with that x, I multiply the whole thing here. So x times 1 is x. X times negative 1/2 square is negative 1/2 x cubed. And x times that is 1 over 24 x to the 5th. And then we just combine them. But of course we not combine them, we subtract. To subtract, we change the sign of everything here. Negative to positive, negative to positive, positive to negative. And then we combine. X and x cancel out. 1/2 minus 1/6. I'm sorry, minus 1/6 plus 1/2. Same thing though. So that's 1/3. And 1 over 120 minus 1 over 24. Negative 1 over 30. Right. Because tangent is actually an odd function, so in this case we don't really need to leave the space for the placeholder. But if the function is neither, we might have both odd and even function. Right. Next, divide the highest terms. 1/3 x cubed divided by 1. Of course, it's 1/3 x cubed. And I will take that, multiply the whole thing here, and write that below here. 1/3 x cubed times 1 is 1/3 x cubed. Multiply this 1/3 times negative 1/2 is negative 1/6. Of course, we can continue. Just divide by the highest power terms. Whatever number we have, multiply it back right here and then subtract. To subtract, of course, we change the sign to negative, from negative to positive. That cancel out will be 0. Now, negative 1 over 30 plus 1 over 6. Fraction 2 over 15. And then when we divide 2 over 15 x to the 5th divided by 1, we're going to have 2 over 15 x to the 5th. Of course, we should write this further, but we want the first 3 non-zero term, which is 33. So we're done. But that's the idea. Take the highest power, divide them, whatever we get, multiply by the denominator as a series, then combine them, and then keep divide the highest power term only, and then just keep going. I mean, I should not say the highest power term, the leading term. Of course, we write in increasing order. Right, so that's how we divide them. In reality, we don't have to do much dividing, because it's for the power series. I think it's just multiply. It's a lot more common. So, one more example. How do we do sin x times cosine x? Let's do that again. Right. Before we go to that, I did mention that tangent is an odd function, so that's why we should have just an odd degrees. Right. Now, write the first 3 non-zero terms of sin x times cosine x. Right, we have sin x times cosine x. Apparently, multiplying power series is one of the important tools that you need in this section. So that's why we have one more example here. Right, sine is an odd function, therefore an odd series. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial x to the 7 factorial. Cosine is an even function. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Right, I change the fraction first, do the evaluation of the factorials, and then we multiply them. X, this is 1 over 6. 5 factorial is 120. Seven factorial. By the way, on the calculator, hit 7, and then math or on the way to probability tab, go down to factorial. That's what we have. Hopefully we don't need to go this far. Right, 1 minus 1/2 x squared 4 factorial 24, 6 factorial 1 over 720 x to the 6. Right, now multiply. When we multiply, can we have any constant? And the answer is no. If we start with x, the lowest power is 1. If we take x multiplied by any of this, we won't be able to get constant. So the lowest possible one is we just have x. So take x times 1. Right. Actually, we have to kind of combine like terms and do it like this. And then later on, it will get a lot messier. Now you just have one term and then two terms. Could be 3, could be a lot more different combination. So that's why we have to be careful. And then, so to get to x, because we cannot get to constant, so we just have to get to x. Get to x, the only thing that possible get x is that x times 1. Now, can we get x squared? If we want x squared, we can start with x, multiply by any of this. We cannot get to x squared, right? If we take x multiplied by this, we can only have an odd power, so cannot get x squared. Right, too bad. If we cannot get x squared, can we get to x cubed? Right. Now if we start with x, how do we get to x cubed? To get to x cubed, we can take this x and multiply by negative 1/2 x squared, because x times x squared is x cubed. That gives us an x cubed. Right. So that term is good. Now if we take this term, multiply by any of this, which one gives us x cubed? Of course, I have to multiply by 1, right? So potentially, we can have the negative 16 x cubed times 1. These two terms we give it x cubed. Next, we have x cubed, right? By the way, if we go done with that, the next term is x to the 5th. It's not going to help. Right, can we get x to the 4th? If we take x multiplied by this, won't be able to get x to the 4th. Take that multiplied by this, won't be able to get x to the 4th. Take this one, that's too big already, won't be able to get x to the 4th. But we can get x to the 5th. How do we get x to the 5th? Right, to get x to the 5th, we can start with this x and multiply by this guy. X to the 5th. And then if we have negative 16 x cubed, we can multiply by this negative 1/2 x squared to get x to the 5th. That's still x to the 5th. Or we can take 1 over 120 x to the 5th times 1. So those are the combination that give us x to the 5th, right? So we just have to go with constant. Can we get constant? If not, go to the next one. And every time we try to figure out the power, try with the smallest power first, and then find which one will give us that power. Then go to next, which one will give that particular power. and go to next one, which one will give us that particular power. Right. Now this gives us x, negative 1/2, negative 1/6. What's that? Negative 1/2, negative 1/6. And that is negative 2/3. X cubed. And now this mess, 1/24. And multiply this, we have 1/12. Right? 6 times 2 is 12. And then plus 1/120. Two over 15. X to the 5th. Those are the first three terms. By the way, notice that they all odd powers, right? So as the product is going to be an odd function. So that is one way to do that. A more elegant way, we should notice that I have a double angle formula. Sine of 2x is equal to 2 sine x cosine x. So if we want sine x cosine x, we just divide by 2. So sine x cosine x equal 1/2 sine of 2x, right? Divide by 2. So at the beginning of chapter 8.1 or section 8.1, we did have the power series for sine of 2x. So that, of course, the Maclaurin series, we can actually just use that. If you don't want to use that, let's look at this table. If we look at this table, sine of, we just replace the x by 2x. That's pretty much it. It's still an odd function, so we have 1/2. Now I write a series for sine, but instead of x, I'll use 2x. 2x. Subtract 2x cubed over 3 factorial. You see, I just replace x by 2x, and then plus 2x to the 5th or 5 factorial, and so on. Right? So that's just a power series for sine of 2x. Now we have 1/2 2x. 2x cubed will be ax cubed over 6 plus 2 to the 5th, 32, x to the 5th over 120, 5 factorial. Of course, keep going on that series. Give us x 8 divided by 12, 8 divided by 12, 2/3. And 1/2, so 32 over 240, 32 on the top, and 2 times 120 at the bottom. Two over 15. X to the 5th. Of course, keep going. You see, those should be the same. Right. So the purpose of this section is just a quick review of what we have as a power series. So first, of course, we need to determine the convergence, because that is, in theory, is very important. Because if it's not convergent, then we cannot use the power series to represent the function, because divergence is kind of undefined. Right, so that's the first part. The second part is how do we combine the power series. So we could take derivative. We could take derivative, or we could multiply and divide. But like I said, the most important when we combine the power series is be able to add the power series, and sometimes we have to be able to change the index like this before we combine the power series. But that in the next section. In this section, just want to do a few things just to get to familiar with how do we work with the power series, like how to multiply them, how to divide them, take derivative, and later on we have to know how to combine power series in order to solve for the differential equation, because the ultimate goal is that we're going to use the power series to write the solution of a differential equation. But that for the next section. Right, I'm going to stop the video here. As always, thank you for watching, and see you in another video in differential equations.